Hello everyone. I would like to create this additional video here to go through some things that I missed in the previous lecture, and but also to cover the things that I had planned to do, but unfortunately I spent too much time probably going through the details of the course and so on and so forth, that we didn't manage to cover the things that I had planned. And but in general, actually, I would like to say that this is quite something that I would like to do generally. It is very important for me to make sure that we do the things we plan, so that we don't we keep up with the lecture plan. So what I would like to do, if there is anything that we do not manage to cover, or we need to do some more exercises, and I would like to use these post-lecture videos to do that, to cover that, so that you can watch it and think about these things. But most importantly, what I would like is that you watch it before the next lecture, so that I will assume that at the next lecture that you watched it, and so you are aware of these things that I've discussed in the video, and so we can move forward. So I think these videos are these post-lecture recordings that I will try to do regularly if needed, obviously. Are a good thing in a way that also they take the stress out of the lecture, and in the lecture we can discuss, do exercises, and so on. And if there is anything that I wanted to do or I missed, and then we can cover it in this way, and the deal is that you have to watch it before the next lecture. So in the next in the video that you will start in a moment, I will discuss some things that I've missed. I realized that I missed in the previous lecture, probably because I was going through the material, and I picked 2 pages at once, and so there are some things that I've missed and I wanted to rectify, and also I wanted to go through the part that I didn't manage to cover, so circuit analysis effectively, and I think there will be situations, and I think this one is one of them, when going through these things, some things post-lecture will be more beneficial for you, in the sense that I can go through them in a bit more detail without having to rush and having the time pressure of the lecture. So I can explain you the exercises better in a bigger detail that will probably allow you to learn faster, and so keep you up to speed more easily. So have fun watching the video, and please make sure you watch it before the next lecture. That's very important, because I will assume that you watched it, and so we will move from the point in the lecture plan that is on Canvas that we had planned since beginning. So please go on and have a look, watch this video carefully if possible. Okay, have fun. We mentioned 2 important assumptions that we will do, and the first one is this one here, that there is no variation in time of the internal charge in any piece of the elements that are involved in a circuit. And this effectively means, if you remember, we said that this brings to effectively, as a result, the Kirchhoff current law. And the other assumption that we did say we will do is that the variation in time of the flux linkage due to any external source possibly existing is actually 0. So, and this, as a result, as we discussed yesterday, brings to effectively Kirchhoff's voltage law. But before this, I wanted to, I completely forgot to define what is current. So I'm sure you know it, but I simply just forgot to do that. So if we take a piece of conductor material, a conducting material, like this one here, there will be some free charges in there, and if we assume that these are moving, then we define current I as dq dt. So the amount of the variation of the number of charges that traverse in unit time the surface, any cross-section A of the conductor. Obviously current is measured in amps, charge is measured in coulomb, and from this definition of current we can also define the current density J, which is defined as the current passing through a certain piece of material divided by the cross-section of the material. And J is obviously measured in amps per square meter. Another thing that I wanted to mention to you that again I forgot yesterday is the fact that is related to electric potential. So if you remember, we mentioned yesterday the definition of electric potential that, if you remember, was related to effectively this equation here. And we did, according to the things we said yesterday, we also said that, okay, so in the situation that we've considered here in this diagram here, so if you remember, we were looking at a simplified, let's say, case, just to make things clear, where we have a uniform electric field and we have a point A and B, and we demonstrated yesterday that then in this situation VA is bigger than VB. Okay. Now, and we ended up also from the integral relation we had started with, we can also, we've showed that we can reverse that relation, and so effectively another relation that is very important is that the electric field is related to the potential through this formula here. Now, the thing that I missed to mention is power. So if a current, electric power. So if we have now a current I that is moving from A to B, so let's go back to the diagram here. So if we imagine there is a current moving from A to B, a current I. So how much is the electric power involved in this process? So we've said that there is a certain electric potential difference between A and B. VA is larger than VB. So we can demonstrate here that the electric power is VAB times IAB. So we can easily demonstrate this, and we do it here because remember that VAB is related to work done in this way shown in this formula. And so recalling that minus the work done from B to A can be actually written as the work done from A to B. So we can rewrite VAB in this way. IAB from A to B is the amount of charge being traveling, let's say, from A to B over a certain time t. And so by calculating VAB times IAB, we can see that this quantity corresponds actually to work done to go from A to B time divided by the time required. This is exactly the definition of power. So this formula here is exactly the power required for the charge to go from A to B. Okay. one more thing that I also forgot to mention was related to this part we were discussing about regarding passive elements RCL. So let's say the brief introduction of these components. And we did say that the capacitor is an element that can store energy, isn't it? We also said that the stored energy can be calculated with this formula. And the reason why, I didn't say the reason why the capacitor stores energy, obviously the reason why it stores energy is because of the charge that is being accumulated at the plates. And this charge effectively creates an electric field, and so the energy stored in the form of the electric field present at the plates of the capacitor. So that is why the capacitor stores energy. Using a very similar argument, and this is the bit that actually I need to mention, we can say the same thing for the inductor. So the only thing is that in the inductor, the energy is stored in the form of a magnetic field now. So if we do, we make similar consideration, we can demonstrate that the stored energy in an inductor is 1/2 Li². Okay, so there is an important difference, as you see, between resistor and, on the other hand, capacitor and the inductor, and this is that the capacitor and the inductor, among other things, also store energy, something that obviously the resistor doesn't do. So from the fact that they can store energy means also that they can give away then this energy. Okay, we will come back to this concept later on. Okay, one more thing I wanted to mention to you relates to the very last thing we touched yesterday, and it was about the transient response of a circuit, and we said that the couple of circuits we were going to ever deal with in this course regarding transient was basically the RC circuit or the RL circuit. So very simple things just to get the feeling and the idea of how we treat these situations. And we said that, if you remember, that in reality we will always deal only the steady state of electronic systems, at least in this course. But it's good to have a look at the transient. So here I wanted, yesterday was a bit rushed, I think, the presentation of this part. So I wanted to go through this once again, and also providing you with a bit more details about this. So let's have a look at the RC circuit. I've added here a bit more details as compared to yesterday. So we have here a switch that can be in position A or in position B. When it is in position A, it is effectively connected to a potential equals 0. You can see here this new symbol that we didn't introduce yet. This is what we call, you obviously have probably seen this before. This is the ground, and it is for us the reference potential. We assume that whenever we see the symbol, that means a potential equals 0. So this means that this point here is at potential 0, but also this point here is at potential 0. Okay, so we have the switch that can be in position A or in position B. We have our power supply, resistor, and capacitor. We set the direction of our current, as we did here, and we name the potential across the capacitor in this way, taking it positive on this top end. And the presence of the switch effectively means that when the switch is in position A, the circuit is effectively this one. We could look at this as the equivalent circuit of that one we started with. So when the switch is in position A, effectively there is no power supply, and the point that was A is effectively a potential 0, and that's what this is indicating here. we keep everything else the same. So we will still keep assume that the current, whichever current is flowing, is we assume that the positive direction is the one indicated by our arrow that we chose. And when instead the switch is in position B, the circuit is actually this one here. Okay, so let us now have a look at the charging and discharging of this capacitor, having a look, at more in detail at this circuit that we just presented. So let's start with the charging process. So with the charging process, our assumptions are that for any time smaller than 0, the charge in the capacitor is 0, which means that the voltage across the capacitor is 0, the voltage difference, and the switch is in position A. So remember that A means that the point A is effectively ground. And then suddenly at t equals 0, what happens is that I flick the switch in position B. So effectively connecting the power supply to the circuit. And still though at time equals 0, I will still have no charge on the capacitor, which means VC0 is actually 0. So these are actually initial conditions, if you like. So by using KVL on this circuit, so the Kirchhoff's voltage law, we can say that if I look at this branch, we could say that the potential difference between this point and this point is V, and this must be equal to, you remember we have to follow now the other path that can take us, so there are two paths that can take us from this point to this point. One is this path and the other one is this path. So, and that's what I'm doing here. So from the first path, the potential difference across the 2 points was V, and while following the other path, the potential difference is R time I plus VC, the potential across the capacitor, which I write as I can calculate from here the current through the system as V minus VC over R. Okay. On the other hand, I know that from the fundamental equations of the capacitor that we discussed yesterday, we know that I is equal to C dVC over the T. But now also I know that I must be equal to this, and so I get this nice equation here in VC. VC is our variable, all the rest are constants. So we define tau RC over equal to RC. And so we can rewrite this equation in a more clearer way, that is this one here. So this is clearly a differential equation, a linear differential equation in VC, first order, and equal to a constant term. So this is a non-homogeneous differential equation, which, as we said yesterday, we solve in this way. And so this is the general solution of the equation. And indeed, if we substitute this general solution into the equation, we can end up calculating B, as I show here. And we still don't have A. So to calculate A, we need to use the initial condition that we've set here above. That VC at time 0 is 0. So if we go and impose this condition, so if in this equation we set t equals 0, we get that, and we had to set it equal to 0 according to the initial condition we had. We can realize that this means we end up with this equation between A and B. So A must be equal to minus B, which since B was V, sorry, this means that A must be minus V. And so in the end, we demonstrated that the final equation for VC of t is actually this one here. And we can calculate the current simply by applying the fundamental relation of the capacitor, C dVC of the t, which will give us this equation here, where remember tau is RC. So if we now make a plot of what we've been dealing with right now up to this point, what we've described. So we have here is a plot of the actual potential applied, let's say, from the source side. So as you can see, for times smaller than 0, the potential was 0 because the switch was in position A. But then as soon as t is equal 0 and above, the switch goes to position B, and so the power supply is actually providing a potential V. And correspondingly, now we have the diagram corresponding to VCT and IT. So as you can see, VCT was initially 0, and then it starts to change and approach eventually V, which is actually the voltage provided by the power supply. And correspondingly, the current was initially 0, but then it suddenly jumps to V over R, and to then start dropping again back to 0. This is, if you remember what I told you, that the capacitor cannot allow a sudden variation of voltage at its ends, but it can allow sudden bursts of current, and this is our sudden burst. As you can see here, there is a sudden variation of current in the circuit. Okay, this is the charging. Let us now have a look at the discharging process. So in the discharging process, here are the assumptions we are making. So for t smaller than 0, we assume that the switch was in position B. So it was connected to the power supply V, effectively. So the capacitor is fully charged, which means, according to C equal Q over V, that Q, the charge on the capacitor, is C times V, and correspondingly that Vc is effectively V. V is the power supply value. And then suddenly at t equals 0, what I do is I flick the switch in position A. So basically removing, if you like, the power supply V from the circuit, and so we go into this situation now. So we have the capacitor fully charged, but we've removed the power supply. So let's see what happens in this situation. And the initial conditions are that initially, obviously, the capacitor is still fully charged, and this is expressed in this way. Okay, that VC0 is equal V. So we do exactly the same that we did before. So we apply KVL, and so now we have no power supply, so we can write 0 equal R times I plus VC, and so we can calculate the current I, and we can also now use again the fundamental equation of the capacitor, and this time obviously this will be equal to this term, as you can see. So the differential equation is much simpler, is now an homogeneous differential equation, and the solution of this equation is of this form, as we can see here. Okay, and now we can find A by imposing the initial condition, and so A must be equal to V, and so finally we find Vc of t and I of t. Okay, exactly follow the same approach actually that we did before, and here are our nice plots this time. So we have the plot of the actual voltage applied to the RC circuit, which was, as we said, initially was V, and then it dropped suddenly to 0 at t equals 0, and correspondingly Vc was initially at value V, was fully charged the capacitor, and then it starts dropping as it is discharging towards 0, and correspondingly the current was initially 0 because obviously the capacitor was fully charged, so there was no current flowing in the circuit, as we found out in the previous charging section. And what is interesting now here is that the bursting current is negative. So as you can see, there is this sudden burst in current, and then the current again tends to reduce to zero. Okay, this is how we analyze the transient in the RC circuit. We can actually do something, as I said yesterday, exactly similar for the transient response of an RL circuit. So very briefly here, I've drawn again, our circuit with the switch and so on and so forth. I'm not going through the details of the analysis. You can just see it on the video. And finally, the final equations are those here. So for the charging bit and the discharging bit. So you can see that tau in this case is L over R, and charging and discharging takes this form. So what is important to note now is that these equations look in a way swapped as compared to those that we obtained for the capacitor. And this is because, as we said, the inductor does not allow sudden variations in current. It does allow sudden variation in voltage, and so that's why they have this form. Okay, so this is more or less where we left things yesterday. So I would like to go on now and talk about the other things that were planned for yesterday. So the first thing I wanted to mention to you is inductively coupled circuits. So we've seen the inductor, we've seen the fundamental equations that we discussed. So let us now consider the situation where we have one inductor next to another inductor. So we have effectively two, say, circuits, circuit 1 and circuit 2, and these two inductors are near to each other. So as we said, Fe is the flux linkage due to the current that is flowing into the inductor, which creates a magnetic field, which creates flux linkage, which ends up in the end creating voltage across the inductor, and so on and so forth. This is effectively the flux linkage caused into circuit 1 by the current flowing in circuit 1. So we shall call that Phi11. Okay, this is the flux linkage in circuit 1 due to the current in circuit 1. In the same way, we can define Phi22 as the flux linkage in circuit 2 because of the current flowing in circuit 2. We clearly understand that at this point there are also two possible other flux linkages at play here, because obviously the current flowing through the inductor L1 will generate a magnetic field which will be detected, possibly will be felt, if you like, by also the second circuit. And in the same way, the current I2 flowing into L2 will generate a magnetic field which is detected also by L1, by circuit 1, which will so this immediately means that we have mutual flux linkages, Phi12, which is M12 I2. So Phi12 is the flux linkage in circuit 1 due to the second circuit. Where M12, we shall call it as the mutual inductance. Okay? And the same way we can say that there will be some Phi21, a flux linkage in circuit 2 because of the current flowing in circuit 1. And so this will be written as M21 I1. So we can demonstrate that actually in these circuits M12 is equal to M21, and so we can actually use the term M as we did in the drawing here. And so finally, what we can write is that by looking things from circuit 1, if I wanted to calculate VA minus VB, or VAB as we know, we should call it, for example, V1, the voltage at the terminals of the circuit 1. This is using the fundamental equations of the inductor, is L1 di1 dt, and plus now the term caused by the mutual inductance, which, remember, is the term we need to consider is phi12. And so according to what we've done for the inductor, we need to consider the derivative, if you like, of the flux linkage, and so this effectively end up showing up in this way. So M di2 dt. In similar way, we can write down the voltage seen at the other side of the circuit, so V2, which is VCD, and this also appears as L2 di2 dt plus the term related to the mutual inductance, M di1 dt. So you can clearly see that these equations show the fact that what I see in one circuit is actually dependent from both the current in that circuit and the current in the other circuit. Okay, and this is exactly indicating that these two circuits are interacting through the magnetic field. Now we can demonstrate that it would be that we can write down M in this way. So M is equal K times the square root of the product of the two inductances at play, where K generally is between 0 and 1. When K is 1, we will talk about perfect coupling. And this is the situation that effectively we have in a perfect AC transformer that we will briefly mention later on. The important thing is that when we are at K equal 1 condition, that effectively there is perfect coupling between the two circuits, then the circuit as a whole is storing zero energy. This is the fundamental condition for the transformer. So the transformer is not storing energy. Whatever energy is pumped, for example, into circuit 1 goes out into circuit 2, and so on. So this is a very fundamental result that is worth keeping in mind, just because it's something that we may use later on. Now, just still on the fundamental components, I wanted to mention to you that what we've seen previously when we introduced the equations of resistors, capacitors, and inductors, those are the ideal components. Real components, though, are a bit different, and they're more complicated, let's say, to understand. And here what I wanted to show you is what we call equivalent circuits of real components. So for example, the real resistor, how could we represent it using ideal components? So here are two representations, if you like, of a real resistor using ideal components. So a real resistor could be represented from the circuit point of view as a resistor with the same resistance of the resistor that we are dealing with, but it has in parallel an ideal capacitor, CP, C parallel, and a series inductor, LS. The value of these extra elements, CP and LS, obviously depends on the resistor, the technology that has been used to make it, and so on and so forth. There is also another possibility, is to draw the equivalent circuit of a real resistor in this way. So it is very important to know when we use real components that when we think that, for example, that we are using into a circuit something that will behave like the ideal component R, well, we need to keep in mind that this is not true, and that in reality what we are using is, for example, something like this. Okay, so just keep it in mind. It's something to always keep in mind, this separation between ideal and the real. So same thing, same story for the capacitor. So for the capacitor, we have a capacitor that is exactly has the same capacitance as the real capacitor we are planning to use, an ideal capacitor here, but it has in parallel a resistor Rp and an inductor Ls. And same story for the inductor. So the real inductor is actually an inductor that has the same L as the inductor we are planning to use, but it has in parallel an ideal capacitor Cp and an ideal resistor Rs. Okay, let us now define some fundamental concepts related to circuit analysis. So let us consider this circuit here, which is, as we said, an ensemble of components connected together and conductors. Let us see here some of the definitions we will need. So what do we define a node, a principal node? Principal node is a junction between 3 or more conductors. We had anticipated that already yesterday when we were talking about the Kirchhoff's current law. So here we have these principal nodes would be, for example, this one here, node A and node B. Now, there is also another node that we always need to define. This is this so-called the reference node. In this case, this reference node is this part of the circuit here. You can see that this point and this point are actually equipotential in this case. So we can actually assume that this is one big node, and this is actually our reference node. Okay, we will see later on how we use this information. Then we have a branch. What is a branch? What is a loop? A loop is a closed path in the circuit. So obviously in a circuit like this one here, there are many loops available. There is this loop, there is this loop here, there is this loop here. Okay, so there are many different loops, and we can define also what is a mesh. I will go to the branch in a moment. A mesh is a loop that cannot be decomposed into smaller loops. So in this case, as indicated in the diagram, a mesh is this one and another mesh is this one here. They cannot be decomposed. So this part here is a mesh and this part here is another mesh. You can see that these two meshes share a branch. A branch is a path containing series connected elements joining two principal nodes. Okay. Finally, a port. This is something we will come across later on. A port is two terminals to which external circuit sources can be connected to. So in this case, for us in this circuit, a port is this part here of the circuit. Okay, so just to clarify now, so when we have a circuit like that, what is the target? Well, the target is to find all currents flowing in any point of the circuit and to find all voltage differences across all elements of the circuits. Obviously, remember that conductors are supposed ideal and so equipotential by definitions. Conductors, metals, if you like. This comes from Gauss law and whatever you've done in electromagnetism. And so in a circuit like that, for example, the target is to find all the currents indicated and all the potential differences across all the components. So let us see circuit analysis a bit in action in a very simple manner. So in this case, we will use very basically KVL and KCL. So let us see some practical circuits, so and very fundamental also. So the voltage divider, for example. The voltage divider is this very simple circuit that I can show you here. It's effectively two resistors connected in series and attached to a power supply. There is only one mesh here, as you can see, and this one here indicated here, and the direction of we are going to move along this mesh is the one indicated by the current I that I've indicated there. So we apply KVL in the way that we've said previously. So in this case I write V, so it's the potential difference between this point and this point along this path, equal to, again, with the potential difference across between this point and this point across now this path. And so this is, according to the things we've discussed, this is R1I1 plus R2I. And so we can calculate I. And so we can now find V2 as indicated. V2 is this voltage difference across the resistor as indicated. And so V2 is given by this formula, R2I, which is this one here. And so we can see that the voltage divider says that if you want to find the voltage across R2, you take, this is effectively given by the resistor R2 divided by the sum of the two resistors multiplied by the voltage of the supply. So this nice little formula here. So these are nice little things to remember because they are continuously useful. So it would be ideal if you could try to remember these empirical, let's say, results. There is one thing I wanted to mention, though, about the voltage divider, because it would seem here that, okay, so how much should be R2 and R1 that we should choose? Obviously, we have two variables, and this is only one condition. Let's say that I wanted to have V2 equal a certain value. So obviously this condition by itself won't set R1 and R2 at the same time. So in general there will be more constraints to use, and one, for example, to use is a power constraint. So we could, for example, say that the power provided by the source in this case is V times I. V is the voltage of the source, I is the current flowing in the circuit. Since we know the current flowing in the circuit, which we calculated here above, then we can easily calculate the power provided by the source, which will be this one. And we could say set a constraint that, because we know that the source can provide only so much power, that is, let's say, K, so this means that this value has to be smaller than K. So this is giving us a second condition, and so we can use this condition together with the one related to the voltage we want, V2, and so we have this is the power constraint condition, and this is the voltage that we want to get out of the voltage divider. And so if we fix a little bit the system of two equations into variables, we realize that effectively it is a system in this imposing that the sum of the two resistors has to be satisfy something, while the ratio of the two resistances has to satisfy something else. And so we can solve this to find R1 and R2. Okay, another nice application still on voltage divider, as surprising it could be, you can make a voltage divider using two capacitors now. So if we use this circuit here, and we have V2 here that we calculate again using KVL. So we have, this is a KVL relation, V equal V1 plus V2. Remember that the fundamental equation of a capacitor is C equal Q over V. And so using that applied to the two capacitors, noting that in a series connection of two capacitors, because these two capacitors are effectively connected by an equipotential conductor, this means that if on this plate I have minus Q, on this plate must be also plus Q. So this means that we have this situation of charges at any time across the two capacitors. And so this is the key, let's say, to find a solution to this circuit. So as you can see here, I wrote that V1 is Q over C1, V2 is Q over C2. I remember that voltages are always taken in this way, and so we can finally end up writing that V is equal to, according to KVL, using KVL and using these two relations here, we can write this equation, noting that this is what we've called the 1 over C dot when we define the capacitor, and we remember that Q, since we are interested in finding V2, which is this one here, I will express Q in terms of V2, and so we end up with this formula here, which we simplify, and so in the end we can demonstrate that V2 is C1 over C1 plus C2. As you can see, this formula is very similar to the voltage divider formula we found for the resistor. The only difference is that here, if we want V2, which is the potential at the two ends of the capacitor C2, the numerator is C1. So that's the only difference, let's say, with the corresponding formula for the resistor. And finally, I wanted to mention to you another divider, which is the current divider this time. So we can make a current divider by considering the circuit here. So two parallel resistors connected to a voltage supply. So in this case, we will use KCL. So we have a principal node and our reference node here. So we write the Kirchhoff's current law for this node here, which is indicated here. So obviously, the first thing we do is obviously we set current directions in all branches of the circuit, as we did here, as you can see. So I in this branch, I1 here and I2 here, and so we write that KCL is this formula, is given by this formula. And so we have that, we remember now that the fundamental formulas for the resistor, we have V2 is equal R2I2, same for V1. So we substitute these things. We remind, first of all, that because the two resistors are effectively at the same potential, isn't it? So the potential difference between these 2 points is the same. So we write that V2 is equal V1, and so we can calculate I1 as a function, for example, of I2, which we substitute into the KCL relation that we had found earlier, and so we find an equation for example, finding I2. Obviously, note that here, because I wanted to find, for example, I2, I expressed I1 as a function of I2 here. So this will allow me, once I go back to the KCL relation, to find an equation just in I2. And so I can find an I2. As you can see, I2 is R1, so it's the resistor of the opposite branch divided by the sum of the two resistances. Okay, so these are nice little formulas to remember that, you know, it simplifies things in analysis in certain situations. So let us now see more in detail some more general techniques that are suitable for maybe more complex circuits. So as we noticed, KVL and KCL, one uses meshes, one uses nodes. So let us see more detail the mesh method, what we call the mesh method. So we need to first of all identify in a circuit all meshes. So say that there are m meshes in a circuit. Then we have to assign the current in each mesh, sorry. And so let's say that these are I1, I2, IM. So once we do that, we write the KVL for each mesh. This will give us a system of m equations in m variables, the currents, that we will solve. So for example, in general, we could say that the system of equation will look something like this. So we will have for the first mesh a term in front of I1, which we shall call, since it's the first mesh and refers to I1, as R11 plus R12 I2. So this is because it relates to the first mesh and it's connected to I2, and so on and so forth. So era 1m IM equal to whatever voltage sources are around, V11. Okay, this can be a combination of different sources that are in the circuit. So we can demonstrate that any circuit we have, we can always end up with a system like this. And this system can actually be solved very easily using a matrix approach. So this technique, as you can see, is extremely powerful to be implemented if the circuit is obviously complicated, to be implemented via using a computer. So you have, a matrix of resistances, a vector of currents, a vector of constant potentials, and so you solve it. So for example, let us see this in a very simple situation when we have a two-mesh circuit. So let's consider this circuit here. We will actually keep using this circuit all along in all the other methods, just to show that every method is actually equivalent and simply changes the way we approach it, but the final results are obviously always the same. So let's say that we have this circuit, we've identified the two meshes, we choose the currents, sets the direction of rotation inside the mesh. And let's say that the target in this circuit is to find the potential between B and D. So we want to find VB minus VD. So we write KVL in circuit in mesh 1 and KVL in mesh 2 using what we said. Remember that here the branch BD is shared. Okay, so as you can see, this is taken into account into the KVL that we are writing down. So you see in R3 there is current I1 flowing in this direction, but also current I2 flowing in this direction, and that's why we have this term here, and similarly in the other KVL. So from the first equation, we can write the first equation in a fashion that resembles more what we said previously here. On one side all the currents, and the other side the constant voltages present. So as you can see, that's exactly what I've done here. So we have a constant equal to a number in front of I1 plus another number in front of I2, and the same for the other equation. And now we can solve this. This is a system now of two equations in two variables, I1 and I2, that we can solve. The solution is a bit lengthy, so you can. I won't comment. I will just give you it's just algebra, so I will just point out what I've done very briefly. So what we can do, for example, I want to use addition or substitution to eliminate one of the two variables. So what I do here, for example, is I take the second equation and I multiply it by this term. This will allow me to eliminate I1 from the system. So as you can see, I've done the multiplication here. So this is what I obtain by multiplying the equation 2 by that term. So and I subtract 1 I do the subtraction equation 1 minus 2a. So I do that, and I obtain this equation here. And we note that this term is actually can be simplified. And if you do the calculations that I'm showing you here, you can see that this becomes this term. And as we did when we mentioned the resistor and when we connect in parallel resistor and so on, we can see that remember that R1 in parallel to R2 in parallel to R3 is actually this one. Okay, so from this point to this point, note that what I've done is simply I've made appear here R1, R2, and I've multiplied also the numerator by R1 and R2. The reason I've done this is that by having R1, R2, R3 in the denominator of this thing, so R1, R2, R3, all this is effectively this thing. So this is the trick. So it's all sorts of algebraic tricks in here at play. So never mind, in the end, what I get is that after some algebraic steps, I get the final result. That is I2. I found now I2. I now do go and find in a similar way I1. I won't go through all the steps. You can watch them on your own by stopping this video probably. So, and in the end I find I1, which is this one here. And so finally we can calculate VBD, which is R3 times I1 minus I2. Remember that there are two meshes, so two currents effectively passing through R3. And so if you do all the calculation, you end up with this formula. So this is VBD. So here we've illustrated the mesh method. Let's have a look now at another method, the nodes method. So the general idea is that, first of all, we identify the principal nodes. Say that they are NT. Then we identify the reference node. Okay, so this means that the reference node is the node that we assume is at ground potential. Okay, so it's our zero for the potentials. So really the independent nodes for us are NT minus 1. Then we assign all the currents into the independent nodes. And then we apply KCL at all independent nodes. And also we apply KVL on each branch to express the current in that branch as a function of circuit elements in that branch. So let us apply this method to the previous circuit. So here we have two principal nodes. These are B and D. But D will be our reference node, the one that we assume is at ground. So effectively I could also draw here our ground symbol. So really there is only one principal node, which is B. So I will draw all the currents that are on the branches that are connected to B. So I1, I3, I2 in this way. And so now I can write down KCL for the node B. We write KCL, so I1 is the only current going in, equal the sum of the currents going out. And so now we consider the branch BAD. So we consider this branch. And we apply KVL there. So we have that V in this point, VB. We could also read this as VBD because we said that D is actually our reference potential, is equal to minus R1 I1. Remember, you see I1 goes in this direction. So, but I'm moving from B to D. So I'm taking this VB minus VA. And so this means that the potential difference across R1 taken this way is actually minus R1 I1 plus V1. So this is taken from this point to this point. And so I can write I1 as I do here. And then we look at the branch BCD, and so B, C, D, and so we apply KVL in this direction, and so we can write that VBD is actually equal to R2 I2 plus V2, and so we find I2. And finally, we take the branch BD, which is this one, and so VBD is also equal to this. And so anyway, what the idea is that we express all the currents in terms of what is on those branches. And so we substitute now into the KCL equation to write this equation here, where, as you can see, the only unknown is VBD, which we can now solve, and we get the final result. That is this one. So as you can see, for this specific circuit, it would seem that the nodes method was much faster, much simpler. Let's now see another important concept that relates to linear time invariant system. So in presence of multiple sources, the current or the voltage difference in any point of the circuit can be actually obtained as the sum of the effects of each single source taken independently, where when all the other sources are considered absent, which means that the voltage sources are replaced by short circuits and current sources are replaced by open circuits. This is what we call the superposition method. This is something that you've probably used thousands of times in your first year physics when you were dealing with multiple forces and trying to solve problems. So the total effect is equal to the effect of each single one added together. So that's what the superposition principle is about. Please remember that the superposition is only valid for linear systems, okay? Because that's the whole idea of this superposition process. It's only true if the system is linear. If you can decompose the response to each of the system to an ensemble of sources as the sum of the responses to each single source independently. So remember, it's only valid if the system is linear. So let's see this in action on our circuit that we've used previously. So say again that we want to find the VBC and we want to use the superposition method. So what we do is, first of all, let's find the effect of just V1. So what we need to do is to consider the circuit as if V2 was absent. And since V2 is a voltage source, we will replace it with a short circuit. So we consider this circuit and we calculate, we try to find VBD. So for example, what we can do is apply KCL, sorry, this is wrong, KCL, in B. So this is our node. And so we have this equation, we again same story, we find I1, we find I2, we find I3, which we express all in terms of VDB, as you can see. And so going back to KCL, substituting some algebra, blah, 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 blah. And so we can find finally that this formula, as you can see, this is VBD just due to the source V1. We now find the effect of V2. And we use exactly the same approach. We replace V1 with a short circuit, and so we can apply KCL and so on and so forth, similar approach, algebra, and so on and so forth, and we obtain VBD as a function of just V2, so the contribution to VBD due to V2. And so we now find the total VBD as the sum of the contributions due to source 1 and to source 2. And so we find the result that we've also seen is valid. This is the correct result, as we've seen also with the mesh node and the nodes method. So this is the superposition method, which is quite interesting, but remember it applies only to linear system. And now let us have a look to another very important theorem, which is the Thevenin theorem. So this theorem says that if I have any complex circuit attached to something, a load, that we shall call RL, this complex circuit could be, if it is linear time invariant, could be represented simply by an equivalent circuit like this one, where this is we call the V Thevenin, so the Thevenin power source, voltage source, and R Thevenin is the equivalent Thevenin resistance. So note that from this equivalent circuit, what we can immediately see is that VTH is actually VAB, when obviously RL is not connected to the circuit. We are in this open circuit condition, because obviously there is no current circulating in the equivalent circuit. And R Thevenin is actually the resistance between A and B that we see when we look our complex circuit from AB. So imagine that you take this complex circuit and you look from A and B, and you ask yourself, which is the resistance that I see in front of me? Well, that resistance is what we call R Thevenin. Okay. So the approach in applying what we've just very simply described is that we first of all separate the circuit that we want to simplify from the rest. Okay, so in this case, in the case of this circuit, separate the circuit that we want to simplify. So this is the circuit we want to simplify. And then we need to find the equivalent Thevenin resistance by shorting all voltage sources and opening all current sources. This is what we have to do to find our Thevenin. And then we look at the final circuit that we get, and we calculate, this will be just a combination of passive elements, and we calculate the total resistance or impedance, we will see. And instead, to find V threshold, what we do, we just take that circuit that we have, we want to simplify, we do circuit analysis, and we find the voltage at the terminals A and B. Remember, these are open circuited; they are not connected to the well, in the case here above, to RL. Okay, they need to, A and B need to be considered open circuit. So let's see an example again on our circuit that we've been using all the way up until now, that we know so well. So let us assume that the target here is to find the Thevenin equivalent circuit as seen by R3. So I want to treat effectively R3 as the load resistor for my circuit, and I want to find an equivalent circuit for all the rest. So let me redraw the circuit in a more clever way. You see, I've redrawn the circuit in this way that kind of emphasizes, which is the part of the circuit that I need to simplify. Obviously, this redrawing is possible because you notice that this end and this end are all obviously, this part here, this part here, and this part here are all equipotentials. So I can move this branch to the end of the circuit if I maintain the proper connection. So you should probably easily realize that this circuit could be equivalently redrawn in this way. And so I can now visualize the fact that I need to, this is the circuit I want to simplify. So I want to simplify this circuit. I want to find the Thevenin equivalent for that circuit. So, and here it is. Circuit to simplify is this one here. So let's start finding our Thevenin. As we said, here we have only voltage sources, so we have to short circuit the voltage sources, and that's what I've done here. And we are left with just this circuit, which is the parallel between two resistors. So when I look at this circuit from these two terminals, what I see in front of me is two resistors in parallel. And so the Thevenin resistance is R1 parallel R2. And then we have to find V Thevenin. So the Thevenin voltage, which is the voltage at this end, at these two terminals, between these two terminals, we need to analyze the circuit. So because B and D are open, the only current that flows is in this mesh. This is a one mesh circuit now. And so we can apply easily KVL, and that's what I've done here. So we have basically what I've done is I've considered the potential between this point and this point, which must be equal to the potential across this other branch. And so we have V1 minus R1I, remember that the current here is flowing in this direction, equal to R2I plus V2 in the other side. And so we can calculate the current, and so we can find VBD as simply using KVL on this branch. Okay, so R2I plus V2, and so we substitute, do some algebra as indicated here, and so we get V Thevenin, that is actually this value here. And so the final circuit, the equivalent Thevenin circuit that we were after, is this one. So from the point of view of resistor R3, the rest of the circuit it was attached to is equivalent to these two components, V Thevenin and R Thevenin, where R Thevenin is given by this quantity and V Thevenin is given by this. Shall we check that? So the way to check this is to calculate. Let's find VBD when we attach R3 to the circuit, to this equivalent circuit. We've obviously already calculated previously VBD many times with different techniques, so we know which is the right result. So this is our check. Okay, so let's find VBD. Let's analyze our equivalent circuit here. So VBD according to the circuit is the voltage divider. So it's R3 divided by R Thevenin plus R3 time V Thevenin. So this is the voltage divider formula. If you do all the substitutions, here you can see that I wrote V Thevenin in a quite nice compact way, which we use. And so if you do all the algebra, you end up with the right result. So this is our check. The process is correct. Okay, so please make sure you understand the Thevenin theorem. The Thevenin approach is extremely useful in many occasions to simplify the things using an equivalent circuit as simple as this one here, with just a voltage supply, for example, V Thevenin, and an equivalent resistor R Thevenin. The nice thing about the Thevenin, the use of these equivalent circuits, the Thevenin equivalent circuit, is that this can be applied also to in real life obviously real circuits and circuits that maybe we don't know anything about. This is what I call the black box. Okay. Obviously, there is one important assumption that we are doing when we use Thevenin, and the fact is that the circuit is LTI. Okay, so this is very important. So in a black box, this means that you need to know something about that black box, that it must be made of linear components to be able to do that. But the two concepts we rely on is to use Thevenin in these new terms of using black boxes and so on is this. So the first that we define is the open circuit voltage, which we indicate as VOC. If you've noticed, when we were talking about the Thevenin theorem previously, we actually mentioned that VOC, this open circuit voltage, is actually V Thevenin. Okay, so we've actually already mentioned the term open circuit previously. So the open circuit voltage is the voltage I measure at the two terminals of a circuit when it is the two terminals are open circuited. The other concept is the short circuit current, ISC, and the short circuit current is the current that I measure between these two terminals, when I short circuit them. So let us assume that I have my black box, and I'm assuming that this can be equivalent to some Thevenin equivalent circuit, as I've indicated here. So if I keep the two terminals open, obviously, as we said, the V open circuit is V Thevenin, because there is no current flowing through if there is an open circuit here. But if we now short circuit the two terminals A and B, so if I short circuit them, there will be a current flowing through. This is the short circuit current, and this short circuit current is given by this. And so we can, once we have VOC and we have ISC, thanks to this relation that we've just realized, we can calculate R Thevenin. So this is a very clever way of using external measurements. So I can measure VOC, I can measure ISC, and I can use them to work out the Thevenin equivalent of what is inside that box, using these additional considerations, that VOC is equal effectively to V Thevenin, and that R Thevenin is equal to V Thevenin over ISC. Okay, this is a very clever use of the Thevenin theorem to find the equivalent circuit of something I know nothing about. I only have the two terminals sticking out of that black box. So by doing some measurements, you can do that. Oh, please don't go tomorrow to the lab and short circuit the two terminals of the power supply, because you may actually damage the power supply. In practical terms, the way to use this black box approach to find the Thevenin equivalent is to use some precautions. So use some, for example, known resistor loads to prevent, for example, that the current becomes too large and so on and so forth. So please don't go tomorrow in the lab and short the two terminals of a power supply to find the Thevenin equivalent. So here we have our example. So to try to apply these concepts mainly. So let us assume that we have the circuit we considered previously. And so you can see R3 is our load resistor, and this is the black box. Okay, so it's that we know how it is made of, but I just want to show you how to calculate analytically, if you knew what is inside the box, how to calculate analytically VOC and ISC. So let's try to find. This is what is inside the box. Let's try to find ISC. So to find ISC, we said we need to short the terminals B and D. So I short the terminals, and so what I get is now this circuit. I will redraw this circuit in a way that makes things a bit clearer, which is this one here. So we can see that this circuit is made of two meshes that I will circulate in these directions. So I use the mesh method to analyze this. And obviously these are extremely simple meshes. And we obviously realize that the total current flowing through BD, the short circuit, which actually is this short circuit, is obviously the sum of the two current, I1 and I2. And so from the analysis of these two meshes, I can easily see that so if I analyze this mesh, we can easily find out that obviously I1 is V1 over R1, and from the other mesh I2 is V2 over R2. And the other thing we can do is to find out VOC. So the way we find VOC is, remember that VOC is actually Thevenin, and so to find VOC we have to go back to what was inside the black box, and we calculate, we found out the speed. This is exactly what we did actually previously when we were applying the general Thevenin concept, so I want to do that again. So Thevenin we found was this thing, and so having ISC now and having Thevenin, we can calculate Thevenin. And we can find out that is exactly what we knew it should have been according to the previous analysis we did with the general Thevenin approach. So this Thevenin theorem is extremely important and allows us to simplify enormously circuits. We will learn to apply Thevenin very efficiently. Obviously, our circuits, as we said, are very simple, so it will be I'm sure easy for you to do it. A theorem that is connected to Thevenin is the Norton theorem, which is effectively related to what we just said actually regarding also short circuit current and so on and so forth. So our equivalent Thevenin circuit is this one. We have our load attached to our equivalent circuit. Well, this equivalent circuit can be, the Thevenin equivalent circuit uses voltage sources, ideal voltage sources. So we can redraw this circuit in a form using ideal current sources. That is this one. This is called the Norton equivalent of the Thevenin circuit. And we can easily demonstrate that IN, so the Norton current source IN, is actually Thevenin over Thevenin. This is, if you like, is what we said previously as ISC. So how do we find out about IN? Well, it's exactly what we did for ISC. So we need to think to short our Thevenin equivalent circuit, and so in this way we can find IN, which is V threshold over R Thevenin. And equivalently, how much is this resistor Rn that we need to put there? Well, that resistor has to be R Thevenin, because this is the only way that when these two terminals are open circuited, the current IN will circulate in here, and so we must demonstrate that potential difference between these 2 points when this circuit is open circuit, so we remove this part, this potential has to be Thevenin. So indeed, if you multiply IN by R Thevenin, this gives Thevenin. Okay, so that's why there must be a parallel resistor Rn which has this value. Okay, so this is the Norton theorem, which also provides an immediate relation between the Thevenin equivalent and the Norton equivalent. So this is also useful sometimes to know. The next thing I wanted to briefly mention is the star-delta transformation. This is just something that it's what it is. I won't say anything more about it. It's just transformation between this circuit and this circuit. So we can transform 3 resistors connected in a star way into an equivalent circuit made of 3 resistors connected in a diamond fashion, in the delta fashion. And these are the formulas that provide the elements of one circuit as a function of elements of the other circuit. So it's just something that to know that this exists. We'll probably not even use it, but I just wanted to point it out to you, just so you know. Okay, there is another point to mention, that I put in the references a section that I called mesh versus nodal method. So I won't cover this here, but please feel free to have a look at the references that are provided, and the references point you out, what are the advantages and the disadvantages in using, in certain cases, the mesh method or the nodal method. As I said, our circuits will be generally very simple, so I don't see the reason to do this now. In case we will discuss it together, but feel free obviously to have a look. So the last couple of things I wanted to mention to you is the so-called maximum power transfer theorem. That is a very simple concept, actually. So we've found out that any circuit can be drawn as an equivalent circuit to as this one, Thevenin equivalent, and so this will be then attached to a certain load, say RL. So which is the power transferred or used by the resistor RL? Well, we know that power is calculated by the voltage at the 2 terminals of the component times the current through the component, and so using very simple voltage divider to find VL and the KVL in this single mesh circuit, we can easily find out that this is VL and this is the total current, is the voltage divided by the sum of the resistors in the circuit. And so we end up with this formula, that the total power that is being transferred to the load by this equivalent circuit is this one here. So what we see here is that if we were to plot PL as a function of RL, this would have this shape, as a maximum and then goes down. So we can clearly see that this function has a maximum when the RL is matched to R Thevenin. So this is the very important concept I want you to retain, that we maximize power transfer between a circuit and a load when there is match between the equivalent Thevenin resistance and the resistance, or we may generalize this concept using the term impedance of the load. Okay, and finally, the last concept for today, and to complete what I wanted to do in the lecture, is the concept of real voltage and current sources. So as we've seen that there are real resistor, capacitors, and inductors, also we need to talk about real voltage and current sources. So we've seen what we mean by an ideal voltage source. So we imagine that, for example, this enclosed in this box is an ideal voltage source that has just an ideal voltage supply. And so this means that VAB, so the potential between these 2 points, is always Vs, no matter what is RL that I attach to this circuit. That's the ideal situation. The reality is, though, that the real voltage source is made of 2 components, to the minimum at least, is an ideal voltage source and a series resistance. It's an internal series resistance of the source. And so when we consider the total circuit now, so imagine to attach a load RL, so there will be now a current flowing through the circuit, and this current is, we can call it IS, the current of the source, which also identifies with the current of the load. And we can define also the potential across the load in this way as VL in this case, which also is equal to VAB. VAB is actually the potential that is effectively seen at the 2 terminals of the power supply. So this is our identification, if you like, between source and load. We can identify this, sorry, you can see this right now. So we can do this identification here. So from the source side, the voltage at the 2 terminals of the source is VAB, and the source is giving a current IS. But this voltage VAB and this current IS are actually equal from looking at these things from the load side to VL at the 2 terminals of the load and IL through the load. Okay, so we will just clarify this tiny detail of what is related to the source and what is related to the load, although they are the same. So VAB is exactly the same in value to VL, and IS is exactly the same in value to IL. So what happens in a real voltage source is that VAB in general will be smaller than Vs. So the actual voltage applied to the load will be smaller than the ideal value of Vs. Okay, and the obvious reason is that VAB, according to that circuit of the real power supply, is actually the voltage divider. So the voltage applied to AB is actually the voltage divider, RL over RS plus RL times Vs. And remember that obviously IL, the current provided by the power supply, is actually this value here. So what we see from these 2 equations, and mainly this one actually, is that only if RL is much bigger than RS, then effectively VAB is actually Vs. So it's only if the load resistance is much bigger than RS, or RS is negligible, in other words, then that the real voltage source is also behaves as a good ideal voltage source. If that's not the case, if we are in the opposite situation, that RL is much smaller actually than RS, then to understand what's happening, we should consider the Norton equivalent. We said that the Norton equivalent will actually have this form. So you can see that the parallel resistor to the current source is the Thevenin equivalent of the previous resistor, which is actually RS, according to that circuit. And IN is actually V Thevenin, which is Vs over RS. Okay, so if we consider this Norton equivalent, and we now attach our load, we have a current divider now. So using what we said previously about the current divider, we now know that IL will be this thing. And this thing, if we are in the situation where RL is much smaller than RS, is actually roughly IN, which means, in other words, that in this situation where the load is much smaller than RS, we have a good ideal current source. So the real voltage source behaves in reality like an ideal current source. That's as weird as this may sound. This is what these equations tell us. And this current value is actually Vs over Rs. Okay? That's a quite interesting, I think, realization, isn't it? I would like at this point to conclude, let's say, this part about the real voltage source with something that actually we will use later on as well, the approach at least. And I would like to point out this thing. So we have a real power supply that we can analyze using the black box approach. And so using that black box approach, we have that VOC is Vs, the open circuit voltage, the short circuit current is Vs over Rs, and using KVL for the circuit now with the load attached, we can generally say that looking things, from the point of view using, let's say, labels that correspond to the real voltage source, we could write that Vs is equal to Rs Is plus VAB. You see, what I'm doing here is effectively I'm looking at this circuit and applying KVL to the circuit. So we have Vs, for example, I'm considering these 2 points, so the potential here minus this one here, which is Vs, equal to the potential across this path, which is RSIS plus VAB. I'm not because I'm looking at this equation that I'm writing now with a focus on the source. I'm not interested in writing explicitly what is VAB. VAB are the outside terminal of the source that we will deal with later. So we have this nice equation, which we can put in these terms. Is equal to this. This, as you can see, is as a function of VAB, is a straight line. This is what we've called ISC. It's a constant term, and this is a straight line with as a function of VAB with a slope minus 1 over Rs. The same thing can be done from the load side. So if we look at the load, for the load we can say that definitely these are this is the equation that we can write for the parameters, let's say, that relate to the load. For the load we consider there at least. So VL is RL times IL, and so we can write this equation. Now this equation is what we would call the load line for our load. The equation that characterizes how my load behaves. And so let's try to draw these things now, recalling that IS is effectively for that circuit the same as IL. It's just changing label. Okay, so let's plot I source, which is also IL, as a function of VAB, which is also, remember, VL. So let's plot the IS equation, the formula in the green part, which is this green line here. Oh, by the way, I've also drawn here in red the IV relation if we were dealing with an ideal voltage source, okay? With Vs equal to, obviously, Vs is the value that we've also been using for the real voltage source. And remember that Vs, according to what we've said, is also the open circuit voltage. So the green curve has a slope, as we said, of minus 1 over Rs. As you can see here, I forgot the minus. Remember, here is minus 1 over Rs. And it starts, the intercept is ISC, as you can see here, this value, Vs over Rs. And when from this equation, if I could impose Is equals 0, I would find that VAB must be equal to Vs. And that's what this point is telling us. When VAB is equal to Vs, this line crosses effectively the axis. Okay, so this green line represents this equation. Then I draw also the load line, which is the blue. So this has a slope 1 over RL. VL, remember, is the abscissa, VAB, the independent variable. So this is a line. Okay, so there where the two lines meet, this is effectively the operating point of the circuit. Okay, this is effectively giving us which is the effective actual potential that we will see across the load and the actual current going through the load. And obviously this is a graphical way, if you like, to solve the circuit. And obviously these things we are talking about are actually these values. So VL or VAB is actually this value here. And the IL we've indicated in the graph is actually this value here. So this is a very nice way to approach the same circuit, but solve it in a graphical way. Please note that if the power supply was ideal, I would have had to intersect, to find the intersection with this red line. So this would have been the operating point. Okay, so you can clearly see the problem we face and the difference that the changes that happen, especially to the voltage across the two terminals of the power supply when we go from ideal to real. Okay, and also because RL and RS determine the slope of these curves, you can also here play a little bit and see, you know, what happens when I change these slopes, what happens to the intersection, to this point, where it goes. So for example, we said that when RL is much bigger than RS, then we are close to an ideal voltage source. And indeed, if you do RL very big, this slope becomes small, and so the curve has, you know, goes, the blue curve becomes like that, and the intersection between the green and the blue becomes much closer to this value Vs, which is the ideal voltage of the power supply. Vs. So at the terminals VAB, we would see a voltage that is closer and closer to Vs. On the other hand, please note that the more you approach this point, we also see that the current through the load goes down, obviously, because RL is increasing in value, so the current will go down. Okay. On the other hand, if RL is very big, and so we have, for example, the blue curve is actually like this, you see that we approach now ISC. So VAB, the corresponding VAB, goes down very close to zero actually, but the total current approaches the short circuit value of the circuit. And so my voltage source becomes actually a current source with a total current of close to ISC. That's the thing we said previously. And so these are, please, you know, try to work on this graphical approach, because it tells us all the things that we've discussed actually previously. Okay, so it's a very nice way to approach this circuit analysis, and we will also use it later on, you know, with our nonlinear elements. Finally, similar things can be said in a very similar way for a real current source. So here we have again an ideal current source, and now we are dealing with a real current source. So what happens with a real current source is that the actual current flowing through the load will be smaller than the intended IP because of the presence of this parallel resistor there. Ideally, the parallel resistor should be infinite, but it isn't, and so that's why IL, this basically makes a voltage divider, and so you can see here that IL, the current divider. So using the current divider approach, we can see that IL is indeed smaller than IP, and using really similar concepts as those that I've used previously with a real voltage source, we can conclude similarly, for example, that if RL in this case is much smaller than RP, then IL is more or less equal to IP, and so we have our real current source is actually close to an ideal current source. Okay, and similarly to what we did previously, if RL instead is much bigger than RP, then it becomes effectively an ideal voltage source. Okay, this concludes what I wanted to tell you. Please, try to work on these things.